Alright, time for another DraftScience video presentation. So, nothing to really report. So, comment-wise, or even some sort of counter theory or arguments, nothing. I mean, really, nobody makes physics videos. So anyway, so we won't bother with that, and we'll just go over what some of the new points regarding the double slit. So things that probably they're just facts, you know, of how the math is done and how the calculation is done of what you can understand is the consequence of the experiment and then try to dissect what's causing it. So the path length difference thing is really important, and understanding that the 2 points, the surfaces, whether you believe in a wave theory or in a not wave theory, the surfaces, okay, represent a point source. That means that the stuff, okay, if you think it's a wave, the idea would be it'd be doing something like this, you know, from that center of the surface, and that there would be vectors, okay, in all directions if it was a wave, and if it was particles, scatter would do the same thing, vectors in all directions. Alright, so the important thing is this is something like, we'll just say a half, or traditionally maybe a quarter of a millimeter, this distance between these 2 point sources. So very close, but from a photon's perspective, very far apart. Alright, so what I've pointed out is that the idea that you can sit there and do this, you know, draw some point, you know, in space and say these 2 points, if they were to intersect at this location, it would be the same distance from each one. Okay, therefore it has to be something called constructive interference. That's true, okay, but the catch is that that's happening inside 1/4 of a millimeter. So this image is projected on a screen, traditionally many thousands, or you know, hundreds of thousands of times farther away than the width of the slit. So it's very far away compared to these dimensions. And what we're sort of relying on is the fact that it's being projected, okay, and that projection is an enlargement of whatever we're seeing. It's like a magnifying glass. It's, you know, helping us see what's happening by making it bigger with distance. Well, this doesn't get bigger with distance. Okay, you can't see this bigger. You can only see it smaller than the 1/4 of a millimeter. So it doesn't mean too much. And the lines you're really comparing, the path length difference lines for these 2. So I'm going to get rid of the extra superfluous little bits, and we'll understand that there's really 2. We're creating 2 fans, 2 180-degree arcs at both these points. Their distance is, you know, at their right angles, are not the same place. Now, the traditional math for what the physicists use, they say, well, these 2 lines are so similar, they're so close to each other that we might as well call them parallel. Now, we won't bother trying to figure out that one's a little bit, you know, different than the other one, and that they're converging on a point, right? We're establishing a point in space and saying, do they converge there? Do they converge there? Do they converge there? Do they converge there? We're just going to draw 2 lines and say which one is longer. But they're clearly not parallel lines. They're clearly going to converge, and the convergence is part of this distance. So this is sort of one of the subtle cheats of their math. Now, a big problem is, right, this is a foundational experiment in physics, and what we don't have is a nice chart to go to, okay, where somebody actually did the experiment, even a Stephen Bro type, where they just simply identified what their configuration was. Okay, what did I create as a cause for the effect? just give us clear numbers about what kind of distances we're here and what kind of distance this is, and measure the pattern at a certain distance away. Well, we'll use the traditional L variable. So we need these D variables, and then we need this L variable, and then they can just have it on a scale, and so we can know exactly what the outcome is, and then we can, people can, I can, you can, anybody can then see what adds up here, what math really works and what math doesn't, what math predicts it and what math doesn't. So we don't really have that, unfortunately. You have to really work to go through all the minutia online to see if you can get some sort of accurate chart of a real experiment and the real consequence of the experiment in terms of real numbers, okay, accurate numbers. All right, and so that's a problem. So I would argue that their math is obviously going to be a little bit off because they're cheating the experiment a little bit by not recognizing that this line isn't in the same place as this. They're not parallel lines. So I don't think we'll need that. Just got to use a proper eraser. Let me make a proper eraser for erasing properly. Alright, so I'll be back. Alright, I'm back. Anyway, alright, so these are just observations. These are things I will include as part of the description of the experiment that needs to be understood. So if we understand this is how we're starting, that this one has a length, a distance, and we keep that distance constant for both of these, alright, and say we're going to create a point in space. Well, there's only one point in space where both of them can be, and it's somewhere in here. It's somewhere below this length, okay, somewhere lower, for both of them to tilt in. So we know that's different than what we're trying to establish, is that, we can't make a point where these lines stay the same length, okay, that isn't going to be lower, okay, than what this total length would have been, this line. So we can't go that way, and without going down on a circle. This is the peak of the circle here. This is the radius, and this one's saying the radius is here, and this one's saying the radius is going this way down. So it's obviously going to a new point. So you have to understand it's really just two systems. This is two surfaces, and these are two circles. Both of these are arcs. Alright, so that's a technicality, but it's a sort of important to understand. That's what makes the center one also different, besides the fact that it can't diverge, that it can't get larger with distance. Alright, and so what's the math is basically saying is that we're going to have this effect. Well, the math isn't saying. The theory is saying that the idea is that we want to match the phase. So we want the things happening, the waves, whatever you want to call them, right? We can just draw them as waves. We want the waves to be in the same location in space. So in a sense, the idea could be, see, some people think that the idea is to have them both hit at the same time. But the real idea is I think, is to have this side, one of them produce this wave, right, from here, and this one produced this wave, the second wave, from here. And it's having that sequence recreated, the wavelength recreated, is what you're really after. Okay, so, and for my model, it's obviously just discrete bits of energy, and you just want the energy to be coming at the same sequence. Alright, so you can take these pieces and any one of them could be missing, and you have duplicates essentially. One side is sending your photon, the other side sending the pieces, and the pieces will realign, okay, get rid of the redundancies back into the frequency you're after, the period. So that would happen by a path length difference between the lines. So something that has to travel a little extra distance, a little extra time, means it will be the right distance behind and be able to put these pieces back in order because they're in the right phase. All right. So the path length, you have to understand that this one, okay, is not a parallel line, and that your first path length difference is going to be something like, it has to cross this barrier. Okay, so from this one's perspective. So that's what you have to understand, is they have a there's a difference here. So this one's traveling on a different arc than this one's traveling on, and you're saying the only place it can diverge, nothing can diverge that's in this space. Okay, things pointing this way and this way, they can't grow bigger with distance. It's only when they're both going in the same direction that stuff's going to be part of the fringes. Okay, is only the stuff where both vectors are going in the same direction. That's the only part that has the possibility of growing with distance, because it's doing, this thing, and the distance is getting greater and greater with distance, which means the size is increasing with distance. All right, so it's doing the magnifying thing. Can't magnify inside. Can only magnify things that are going outside. So this would be the first visible possibility for a node, would be the location, you could say right here. And you could have this line. And the argument is to get to this point. Okay, now if I tilted this line, and it stayed the same L, we know it would get shorter. And so now we're really saying, how much do we have to add to that line to get to this point, and whether or not that point is a full wavelength. And that will be decided by how far apart these 2 point sources are, whether that's a possibility. And it is a possibility. You just change this distance and you make it more and more possible. You're basically making the line longer and longer by this being a longer and longer line. And vice versa, I can make this a specific distance. Say if this distance was 15.5. All right, so there was 15.5 wavelengths in this distance. You can kind of automatically see that 15.5 will likely not get me a full wavelength of difference. Now you have to do the math, so you have to do the hypotenuse, square this number, and you're going to get 2.5 as a remainder, and then it doesn't matter what your L is, but you've already got a 2.5 remainder, which is going to sort of guarantee that this isn't going to be a full wavelength. Okay, it's going to be some portion of one. So even some other number might be better, 7.5, because then we'll end up with a 5.0 as what this length of this line will be. It'll have a full remainder, which means it will only be a 0.5 longer, rather than a full wavelength longer. So I can make this spot here either an on or an off. So let's understand, this is just this tiny distance, this 1/4 millimeter. So we're on the screen now. So we'll call this the screen up here. Let's get rid of the extra crap that we don't need anymore. All right. So the screen is very far away, and now everything inside here, this 1/4 millimeter, is still just inside a 1/4 of a millimeter. You're not going to see it. Okay, and we're looking to see nodes that are going to be centimeters long. So this is realistic in terms of the proportions. And the fact is that the single slit does create something that looks like a double node in the center. It has the same proportions as a double. So it's always twice as big, or bigger, or a little bit bigger, a little smaller than twice the size will always be your expectation, and that's because of this starting point. All right, so this is your first. This is where it starts. The experiment on the screen starts right here after 1/4 millimeter, and now you're starting to make your pattern. Okay, your path length differences, and the truth is that your on node will be either really close to that, or somewhere like here or here, someplace. Okay, so these can merge, is the point. They can be a little bit apart, or they could be yeah, a little bit apart. They're always going to be a little bit apart because technically they can't be in here. This space is already filled. And yeah, depending on this number, it's going to be this 0.1 millimeter. This is either going to, so I can make this an on or off. It's completely variable. Okay, 1/4 of a millimeter away just by changing this distance by a half wavelength. I can make a half wavelength more, and then it's going to be a on. I make it half wavelength less total, it's an off. So right at that point, it can be either one. And if it's off, then the first full wavelength of distance will be here or some other location. I can make that first location anything by just changing this number. So in theory, it makes, I think, it explains why there's a double node in the center. Okay, they don't have any explanation. Traditional physics doesn't give you an explanation. So that's the explanation. It is in fact 2 nodes. And the fact is between the laser beam, just shooting through, the photons that aren't affected by the surfaces, just going straight through and diverging a little, and this effect of 2 of the fake node, so to speak, created by 2 equidistant lines. You know, one isn't a wavelength bigger, they're equidistant. So, but they don't go outside of the 1/4 of a millimeter. So that's the thing to it. I can't stress that enough. They can't get outside of the 1/4 of a millimeter. So they're technically, you wouldn't call them a node because they're not being magnified and they're not really fringes. All right. So the point I wanted to raise here was just a way of visualizing this. I've attempted to do it a couple of times, and it's a little bit, imperfect. But you have to see it as you're taking this line and moving it on a circle, and what's happening when you're doing that. So what's helping me understand the concept, all right, is just imagining that process of you're taking this line and you're going to move it to here, okay? So what happens as you're doing that? You can see the arc it creates. All right, well, what's happening when you look at that arc? Well, you start off doing a lot of this way, and you finish by doing mostly this way. So that's the contribution. So you have to think of this line. A little tiny bit of movement gives you a lot of this to start off with. So it's like 90%, all right, this way, and only 10% that way. And by the time you're getting towards the end, you're going 10% the way you want to go. That is getting longer, and you're going 90% in a way that is irrelevant. So that's the big difference. Is you're getting 90% of the motion, like so. So you're making the line much longer here, 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 with a little bit of angular movement. So you move a little angle here, and you go a lot that way. So your line, this line is longer, okay, by recognizing if I put this as the center of a circle, the circle's like this. And so I'm longer outside of that circle. And the further over I go to have so let's say we have a point in space here. So it's the same L distance for this line. Okay, I didn't change its L distance. All right, on its circle, on its radius. So it's still L, this standard distance. And this is the one I want to change by making it go all the way over there. So you can sort of see that I'm now going onto this one's circle. Well, what you can understand is you are making the line longer because you're placing it, you're forcing it to go to a location that it couldn't reach. Let's see how else to say that. It's a better way to say it. But anyway, so the point is, this is just the point that made it illustratable to me, is that just understanding that obviously when you go a little distance here, you're going a lot of distance in terms of the length of your line. It's going to have to get longer in that direction, and that's the direction you're making the line longer in. And that this way isn't helping you any. That's not going to force your line. Doesn't have to be longer for you to go that way. You know, going down doesn't take more length of line. Going that way does. So you're getting more path length difference to start off with. So the pattern, in truth, you know, the objects end up being closer together in the beginning, and then they get further and further apart until it gets very far apart. So it's not consistent. So it means that as you add nodes, you know, little bits, their distance, where you're seeing which ones you're seeing, ends up being you're further along in the arc for a smaller distance. And well, anyway, the idea is that there can be an effect where essentially as the nodes get smaller, the distance gets larger, which means they're getting enlarged more as they get magnified. And so they can end up taking up the same space as an image, but they're not the same in terms of their proportion to each other. So that can be a little bit confusing in terms of measuring the pattern and getting an accurate answer, because you can't be sure either that as you get smaller that you're actually counting where it started. The distance is going to be decided by the first node is a certain distance. When you're first turning here, the first notch, it's a certain distance. Now if I make them so there's even more notches in between those notches, you can understand that maybe I'm not seeing that first one because it's getting blurred out in this blob that's, you know, the first node. Yeah, well, I don't think that's true, so let's not go that far. Alright, so that's probably enough for just understanding that there's no rule that the first node, you know, the center, okay, where they always say this one, so this one's clearly wrong. I think it can be stated that it's clearly wrong to say the pattern is being created at a center, and the center, whoops, center would be in between these two, that the first node is an on, always an on, when it's not. It's really could be an off. It's more likely to be an off because you're already having to go this extra, you know, you're going into that other realm where you're starting to stretch the line, but you haven't stretched it nearly enough, but you're only going a quarter of a millimeter. It's a tiny amount of distance you turned, and it's not enough for you to be constructively, to get a full wavelength. You haven't turned enough to get a full wavelength of distance. So it's more likely that there are two ons, and they're either slightly overlapped or they're slightly apart. But that's the real center is an off. It's just not a very big one, okay? But that's the real center, and the real ons start here and here. Alright, so that's just a fact, I think. That's irrefutable. Alright, now which... Alright, so the basic idea is to just do this path length difference thing all the way around. Okay, keeping one line will be always L, and the other line has to be this distance, you know, added. Hypotenuse of a triangle that has this as a base for this line. So it's always going to be a longer line to get to this one's L line. And so you're just saying that as you go across the arc, you're going to go through these wavelengths. So another way of seeing this, or visualizing it, is if I have something flat, okay, and I put it parallel to you, you know, you can't see any of the surface, but if I slowly start tipping it, you see more and more and more of it. So at first you see one wavelength worse, then you see two wavelengths, then you see three wavelengths, then four, then five, and eventually when you're at 90 degrees, you're going to see the whole thing. And the same thing is happening here. You're going to understand that you're tipping it a little bit. Well, that's not a little bit. You know, if you were looking at it parallel, you're tipping it, and now you see one wavelength worse. You know, okay, and then it's tipped a little more here. Now you see two wavelengths, and it's tipped a little more, and then finally it's tipped this way where you can see every wavelength. And so that's another way of visualizing how if you were at this point, what's happening as you're turning down this 90 degrees. So the point is that Stephen Bro was correct about each one of these quarters, okay, of a circle, a quarter, has that number of wavelengths in the node. So the 180 degrees of the whole pattern would be, there would be twice as many. So if there's 15 wavelengths here, there's going to be 15 nodes over here. That's what you'll finally see when you get to 90 degrees. You'll be able to see all of them, so to speak. The same thing is happening on the other side. So you have a total of 30 places where you can have a path length of difference, where this will be a path length, a full wavelength of difference. Not a path length, a full wavelength of difference, a full wavelength of difference, a full wavelength of difference. When you, at 90 degrees, of course, you have the full wavelength because you have the added distance of exactly what is the distance between the two sources. So when your line finally gets to 90 degrees, it's kind of obvious that you have exactly the number here. And obviously I can make this number 15.5 and it would be an off here, or I can make it 15 with no remainder and it would be an odd. Alright, yeah, so that was the other point to make. And so what else do we have? Oh, alright, so how many point sources. So this theory, right, so they're right in the sense that we're trying to match the wavelength. They're wrong in the sense that these lines are never parallel. And it is important, this extra distance is important. So that's kind of a cheat that they put in their math. And, you know, kind of guaranteeing that they're not going to get a really accurate number. And I guess that's why they've never written down on a chart somewhere, you know, what the pattern looks like. You know, so we would already know what the node size is for a certain distance. It should be something you just look up on a chart, because it's just something you can't change. So we should know that for, you know, 1/4 of a millimeter, and, you know, I mean, it should be in whatever 1 micron increments or something, and we would know exactly what the node size would be for that size separation, because that's all the single slit is doing. So it almost should be something already charted, be something you just look up on a chart, like the sine of an angle or something. All right, anyway. All right, so the single slit experiment versus the double slit. So the double slit, you're just taking these two experiments, you know, and combining them. Okay, so usually it's two the same size slits, right? So you're just saying I'm going to move two single slits. Okay, this is the slit, sorry. Two single slits into each other and create a double slit. And so now the question is whose right angle are we using, right? So we have the same problem, and these are really 4 sources now, and they all have their own arc, right? Each one has its own circle it's creating, you know, in terms of a equidistant line, a line that stayed the same. And what we're really saying is we're going to use one of these lines. Doesn't matter which one we pick. We could pick this one. We're saying the L is going to stay the same on this line. And now the question is going to be, how far does this line have to go to get there? How far does this line have to go? And how far does this line? So we could pick this one, and it'd be the same thing as this one, or this one, or this one. It doesn't matter which one you pick. One of them stays the same distance, and we stay on his curve, and then we just compare how long the lines get for everybody else, and that gives you the right answer. So it's all just a perceptual thing. The point is that these 4 sources are going to decide, all right, the outcome. And to some extent, it doesn't matter how you look at it, but the thing to look at that I think is the only important feature is the only thing you can do is, as we do know, the only thing that really matters is the distance between surfaces. And we know that big distances mean that, you know, the nodes get smaller and smaller, because the longer the distance, the more possible, the more possible turns I can make on this thing, that you would say, okay, there's one notch, there's two notches. I see. So if I put notches on it and I start tilting it this way in your view, and I put notches on it, you'd see the knot, and until you saw all of them. So the more of them I put on here, the more increments, the more places you would say, there, I see another one. There, I see another one. I see another one. So the more of it to see, the more notches there are. So the more wavelengths between 2 points, the smaller the points where you have constructive interference, and the shorter the distance, the less possibility of notching, seeing extras. So they get bigger. All right. And so that rule we could all probably agree on, that's the basic rule. The point sources are close together, you're going to have few notches, they'll be big. You'll have few points where there's a full wavelength of difference. And if I have a long distance between the 2 point sources, then there's a lot of places where there's a wavelength of difference. So that's the basic rule, the basic function. All the math relies on that fact. All right, and so now it's just a matter of interpretation. So what distances are we comparing? And like I said, you can look at the 4 sources in different ways. You could look at the 4 sources and say the 2 lines I'm comparing are, I mean, you could say, if I wanted to match 3, you could say, well, which ones am I matching? Am I matching, say, these 2? Okay, are in phase at this point. I shouldn't draw them inside each other, right? That's breaking the rules. They're in phase at this point. And then I'm going to try to add a third at least. So maybe this one, this distance, or this distance. Right? Now we're just saying, is that distance in phase with this? Is this one in phase? Well, then I have 3 matches, and I'm more likely to have a photon. It should be brighter at that spot. And if I have all 4 of them, well, then I'm really brighter. Okay, and so that's all you're really doing. And so it's really just looking at it and saying, what are you really combining? Are you combining 2 single slit patterns in the sense, should your expectation be, I'm going to get the same pattern I got here. Let's say the pattern looked like this, and then this pattern looked like this. Or should I have the expectation that these 2 things, now I'm creating whole new distances? I just had this distance before and this distance. I now have this distance, I have this distance, I have this distance, and I have this distance, which are the same. These 2 are the same. But I'm just saying I have lots of different distances in there. So I've said as a basic rule in the past, I've certainly said that you just find the shortest distance, and that'll define the envelope pattern, and you find the longest distance, and that'll define the size of the nodes inside the envelope. And I think that rule still holds. So you can do also I've said that the single impediment, okay, is causing the envelope and the slit, the outside surfaces out here, this distance, is causing the small bars. Now this one's probably closer to a certainty. The trick is that you can make this really, really thin. Okay, I mean, you can make it, you can make the slits really thin. All right, and so if I make the bar this size, then the shortest distance technically is this distance. It's not the impediment anymore. So that's the catch. So when the impediment is bigger than the slit opening, then the rule can't be that the impediment is creating the envelope, because it's not the shortest distance anymore between 2 points. So that rule won't work. All right. So you can't, it's not a rule then. But in most cases, you would understand that the single impediment has to fit inside of this distance. So the single impediment will always be smaller than the distance of the outside surfaces, right? It's always smaller than this distance, okay? This distance is always smaller than this, but the catch is sometimes this distance is even smaller. So the idea would be is if the impediment is smaller than the slit opening, then the impediment is deciding the envelope. But if the slits are smaller than the impediment, then the envelope will be decided by the distance between the slits. So just for clarification, but the fact that it's force source math that works, and what you're really just doing is you're just combining two single slit patterns. And the thing to understand is where observationally your brain says, I'm just combining, this slit experiment and this slit experiment. That's what that's what I intuitively fell for. We're just combining these two single slit experiments, when really what we're creating was this single impediment and these two outside surfaces. So these are the two slit experiments we were creating. This single slit, single impediment, same thing as a single slit. This source experiment, and now this new source experiment way out here. Okay, so those are where you have the one big single slit and one small single slit, and that's what we're really combining when you make a double slit pattern. So it's really two single slit patterns. It's just not this pattern and this pattern. It's this pattern and this pattern. So I've said that before. So I think that's where we are now. So the catch is you can't, there's no direct symmetry between the distance between the nodes, which just makes it a little bit like if the nodes were all the same size, it would be really easy to do some calculating, because all you need to know is one of them or the other one. If you knew one of them, you know all of them. So that makes it really simple, right? Because I could just know this one, and then I could know exactly what all the others are going to be. But because of this progressive thing, the fact that the nodes do change and get much bigger here, okay, you can't do that. But this does happen at a constant rate. The curve has a certain mathematical reality that you can also put into your math to compensate, but it's just not as simple as counting. It's not a clock, it's not doing 1 o'clock, 2 o'clock, 3 o'clock, 4 o'clock. It's not even. The positions and the numbers don't match. There's more hours in this quarter, more hours here than there are hours here. Yeah, and so it makes it more awkward. But in essence, their math is dependent on on path length difference, and you really can't change the fact that the path length difference is completely dependent on these distances, and the geometry is inescapable. And if you do make the force source experiment out of the double slit experiment, you can reconstruct the complex pattern. And if you do this, two waves interfering, you have no hope. The vectors, the two wave vectors, will not in any way be coherent to the actual pattern. So people like Stephen Bro should point that out, that this geometry for two waves coming from the center of these distances will fail. This distance will not get you the right answer for a double slit experiment. Going through the middle of the slit with a D variable will not explain either the small nodes, okay, or the envelope. It gets neither one right. Alright, so that should be enough for a video. So that has to be added to my written list, those little improvements. So like I said, critique is a good thing. Criticisms, finding faults, finding errors. But you can do it in some sort of reasonable way, or you can do it as being a complete, obnoxious, insane asshole. And unfortunately, Stephen Bro has chosen the asshole method, and it really makes interaction impossible and not very constructive. So that's unfortunate. But the other people who just say, you're a science denier, that's not helpful either. Because they don't even make an argument. At least Stephen's trying to make one that has, some kind of connection to the reality. So he's done no analysis of their math. He's made no concessions to the idea of 4 sources versus 2 sources. So a lot of this stuff, he won't deal with any of the counter arguments. But half a loaf is better than no loaf. So at least having the argument that the actual pattern doesn't do that, fine, good. It still needs to be explained. And he's not offering any explanation. He's not offering any demonstration that the conventional model works, that it gets right answers. So he's not verifying conventional physics. He's just attacking minutia of my physics. And I can explain why those are legitimate attacks. Those are all places where, yeah, we don't have all of that data yet. But I'm saying it's going to be quite certain that once we do have it, once we do have it, it's no doubt that 4-point sources are what are creating the vectors, and it just matters on which ones you're establishing as being the ones that made the first or the most major contribution. Let's understand, their math is already doing cheats. The idea of saying they're parallel lines, that's a cheat. Okay, it's not the truth, because they didn't want to do the extra complex math to figure out, well, this one has to stay the same and only this one is turning. See, it'd be one thing if they had them both pointing this way, so both lines were getting longer. That's cheating. Okay, the one you have to do is one of them has to stay the same L distance, and one of them has to do all the changing in its length. And they're cheating that argument by using that parallel line math. So their answers won't be precisely correct. They'll be close, but they won't be precise. And this is the same physics that claims it can measure the mass of an electron to 28 places or something. They love doing their little, look how many decimal places we can measure something to. And yet they haven't done any of that strict, careful measurement of this centuries old experiment. Since Newton. It's never been documented, with exact numbers. And there's only 3 variables, wavelength of the light, so that one's, you don't even have to document in a sense. The distance of the opening and the distance to the target. There's not much they have to do here, and obviously the measurement of what happens at the target. Three variables. And yet we have no standard table that you can go to get these answers. I'd say the reason why is because their math actually doesn't work very well, and it would be demonstrated if they actually compare it to the actual results. So if they actually made actual comparisons to actual experiments, they would find their results quite wanting. Not very good. Yeah. Okay. Alright, so enough of a video. So till the next time and such. This has been another DraftScience video presentation. And so till the next time and such.